Welcome to Module 36, Design of Experiments. In this module, we'll cover three-factor full factorial designs. So we'll be introducing an additional factor at two level settings. We'll be looking at all possible combinations so that we can easily study all of the interactions or combined effects. So let's move on. Full factorial design experiments are characterized by having all possible combinations of factors and level settings. Let's take a look at some two- and three-factor designs for full factorial layouts. Let's start with a hypothetical situation. You are now the Popped Popcorn Company of America. You produce bags of popped popcorn. The things that your customers do not want to see in their bags of popped popcorn are unpopped kernels. So this critical to quality characteristic is to minimize or eliminate the unpopped kernels. So your first investigation is to take a look at a two-factor, two-level design of time versus temperature. So A1 would be the low setting for time, A2 would be the high setting for time. Temperature, the low setting is B1 and the high setting is B2. That results in 1, 2, 3, 4 possible combinations of time and temperature. To figure out how many possible combinations you have, we take a look at the number of settings and the number of factors. We have two settings raised to the number of factors, so 2 raised to the second power gives us 4 possible combinations. Let's see if we can make this a little more complex. Now let's add factor C, the kernel type. We could have Orville Redenbacher, and we could have Staff brand. So we have two different kernel types, but we still have time and temperature in our design as well. This results in 1, 2, 3, 4, 5, 6, 7, 8 possible combinations of three factors at two level settings. So that's two settings raised to the three factors gives us 8 possible combinations. So the number of settings raised to the number of factors is the number of combinations or the number of experimental runs. So we would set up this designed experiment, set up the particular scenario of, say, factors and level settings. So let's say that our first experimental combination is factor B at the low setting, factor A at the low setting, and factor C at the low setting. That would be the first combination. The second combination would be C at the low setting, B at the low setting, but now A has been raised to the high setting. And you can see as we march through this design, we're going to continue to use all possible combinations. That's a full factorial design. Now let's take a look at a four-factor full factorial design. Our hypothetical is still in order here. The factors, A is still the time, B is the temperature, C is the type of kernel, and we've added D, the type of oil. The outcome that we are going to measure is the number of unpopped kernels, and we want to minimize them. So all possible combinations, it looks like there's 16 now. 1, 2, 3, 4, 5, 6, 7, 8. And we're going to do it all again for factor D2, the second level of oil. And this gives us the last of our possible combinations. So there's 16 possible combinations when we have four factors at two level settings. So that's 2 level settings raised to the fourth power, or 16 possible combinations. Now this is as large of a full factorial design that we would recommend that you run. Once you get up to 5 factors, then you would be at 32 possible combinations. And logistically, that becomes a very difficult experiment to manage. So typically, 4 factors at 2 level setting is the maximum number in a full factorial experiment that makes sense, 16 experimental runs. When we get into the black belt course, we'll show you how to do fractional factorials, which allow you to increase the number of factors and still study interactions and manage the number of experimental combinations. The following are some experiment design definitions. The first would be a main effect. So that is the effect on the measured outcome that a single factor has when it changes between level settings. Say when we change the temperature from a low setting to a high setting, what's the impact or influence that it has on the measured outcome? A combined effect or an interaction effect is when we have two factors that are actually working together. So that would be the impact that they have on the measured response when together they change between level settings. Like say the time and temperature combination, we may see that that has a combined effect. Say you're making a pizza and we're trying to have it come out to be perfectly done. Well, time and temperature will have an influence and they will probably work together. If we drive the temperature up extremely high, we're probably going to have to minimize the amount of time that we expose that pizza to that heat in the oven. The last thing we have is confounding of effects. We want to stay away from this situation. Now, when we're doing our full factorial experiments, we do not have to worry about confounding of effects. It's only when we get into fractional factorials that we have to worry about this. Confounding would be a confusing between a main effect and an interaction effect, and not being able to tell the difference between which one it is. We'll get into this in more detail when we take a look at fractional factorials in both the Design of Experiments course and in the additional topics that we will cover in the Black Belt materials. Let's design and analyze a three-factor full factorial design experiment. The problem: it takes too long to boil a cup of water in a microwave oven. The objective: determine the factors and the settings that will minimize the time it takes to boil 1 cup of water in a microwave oven. The factors that we are going to consider are factor A, the cover, whether we put a cover on or we don't have a cover. Factor B is going to be rotate, whether we let the container rotate or we don't let the container rotate. And factor C is the location. Do we put the container in the center of the microwave, or do we put it 4 inches off center? We'll have to find out what happens when we try these different factors at their 2 different settings. So this will be 2 level settings raised to the 3 factors. There'll be 8 possible combinations of factor A, cover, factor B, rotating, and factor C, the location. So let's begin. We will now create the design experiment in Minitab. So we open up a Minitab worksheet, and then we select Stat. We select that pull down, and in that we'll select DOE, then Factorial, then create a factorial design. The dialog box that comes up is going to present us with many options. The first one is to enter the number of factors. We're going to have 3 factors in this experiment: whether we have the container covered, whether we allow it to be rotated, or whether it's centered or not centered. Once we've selected that, we're going to display the factorial designs. So there's 2 options here: a half fraction, which would be 4 experiment runs, but we're not going to run a fractional factorial. We're going to do the full factorial. So that's 8 possible combinations. When we have a full factorial experiment, half of the experiment will be at one level setting, half of the experiment will be at the other level setting for any one factor, which means that there'll be 4 experimental combinations for the low setting of one of the factors and 4 experimental combinations for the high setting. We'd like to have about 20 to 25 data points per level setting of a factor. So if we have 5 repetitions of each experimental combination, that'll give us 4 experimental combinations times 5 will give us 20 data points at the low setting and 20 data points at the high setting for the factors when we go to study them. So we're going to select the full factorial, and we're going to enter 5 for the number of replicates. There'll be 40 total data points in our experiment. We're not going to worry about center points, and there's not going to be more than one block. Next, we're going to select the factors. So here we just type in the name of the factor, we tab over, and in this case it's going to be text, so we would select text from the pull down, and then type in the low setting is yes and the high setting is no. And we do that for rotate, and then for location, the low setting is going to be centered and the high setting is going to be 4 inches off center. And we can select OK. And in options, we're going to select do not fold, and we're going to uncheck randomize runs. This way you'll be able to see the same thing on the screen that I'm going to present to you. If you randomize the runs, they're going to be mixed up and they aren't going to look the same as what I have. So just for this particular instance, we're not going to randomize the runs. And then we're going to store them in a worksheet. So press OK. Now from a results standpoint, we don't want to have any printed results, but we do want to have the default interactions, and select OK. Now we can press OK and our design will be generated in our worksheet. So here's the worksheet with our experiment design. We're now going to go through it and organize that worksheet so we can accept data. We're going to add a column, C8, and we'll call that runs. And what we want to do is put this in order 1 through 8. So you're going to have runs 1 through 8 followed by 1 through 8, 1 through 8, 1 through 8, 1 through 8. So what Minitab has done in essence is it's created our full factorial experiment, and then it has replicated it 5 times. So it's the whole experiment in design order, runs 1 through 8, in rows 1 through 8, and then in rows 9 through 16 it's the same thing, 1 through 8, and that's been repeated on down through the design. So we're going to add this column of runs in here because what we want to do is sort the experiment design so that we can key on our data very easily. So the next thing we're going to do is sort it. So go to Data and Sort, and when you pull down the Sort menu, what we want to do is select all of the columns. So C1 through C8, highlight those and select them. And then we're going to sort it by runs, and we're just going to store it back in the original columns. So go ahead and press OK now. So now we have it sorted, and now it's sorted by experimental conditions. So there's 5 run number 1s, then there's 5 number 2s, 5 3s, 4s, 5 6s, 7s, and 8s. And what we've done is we've put the 5 repetitions of each experimental combination, we've grouped them together and we've put them in order. So now when we go to enter our data, we'll be able to collect our 5 data points for the repetitions that we're going to have for an experimental condition, and we'll just be able to key that information in. So now we're going to add boiling time, which is another column, and we've gone out and we've conducted the experiment and we've collected our data. So you can see that we have 5 times, and these are in seconds, the amount of seconds that it took to boil, and we have that data for experimental combination number 1, and we have 4 repetitions of it. So we'll be able to take an average value from each one of these and use that when we conduct our analysis of variance. We are now ready to analyze our design experiment in Minitab. So we're going to go to the Stat pull down, select DOE, Factorial, and now select Analyze the Factorial Design. When that dialog box comes up, it's going to ask us to select the response. So runs is not a response, but boil time is. So we're going to select boil time. Next, we need to select the terms that we're going to analyze in our factorial design. Notice that we have terms A, B, and C. Those are the main effects. AB, AC, and BC. Those are the combined effects, the interactions. Then there's also a 3-way combined effect, A, B, and C. We're going to select all of those so that we have them in our selected terms. So you can use the double arrow to shift them over, and now we have all of them selected. Since the probability that a combined effect of 3 factors is highly unlikely. We're going to leave that out of our experiment design. Next, we select factorial design graphics. So the graphics, what we're going to do is there's an effect plot that we can get in Minitab which helps us to understand the factors that are significant. So we're going to select Pareto and we're going to set the alpha at a value of 0.05. That'll give us a red line on our Pareto chart that is equivalent to a p-value of 0.05, or a 95% confidence that there was a difference when the factors changed between level settings. And that's all we're going to select on that dialog box. Next, the results. We want to have the coefficients in the ANOVA table. We don't need to look at an alias table, and we just want to make sure that all of the selected terms have been selected. ABC and all of the interactions, AB, AC, and BC. And then press OK. And now we are ready to conduct the experiment analysis. So we're going to press OK, and the first thing that you will see will be that Pareto chart. We will now review our analysis results. The first thing we get is the graph of the standardized effects. This Pareto chart sorts all the factors and the interactions in order of significance. The line of demarcation, the red line, that is equivalent to a p-value of 0.05 or a 95% confidence. We can see that all of our main effects and our interactions are all at least significant at that level or greater. Let's take a look at the analysis of variance. That's in the session window. In the analysis of variance, the first one that we want to take a look at is at the bottom of the page. We can see the p-values for the main effects and the two-way interactions. Those p-values are much less than 0.05, so we know that they're significant. If we look at the analysis of variance that's at the top of the page, that gives us all of the separate terms listed out, and you can see the p-statistics associated with them. And we see that the main effects all have p-values of 0.000, and we have the actual p-statistics for each of our combined effects or our interactions. The combined effects are all significant at least the 95% confidence interval. They will take precedent over the main effects taken by themselves. So we're going to use the results from the combined effects to guide us to the best settings for these factors now that we know that they're significant. The next topic is consolidation of results, or pooling. Now typically we run an experiment and we are going to have some factors that are not significant, and they would then get pooled. In our case, all of our factors and interactions were significant, so we kept them in our model. In experiments with an increased number of sources, a consolidation of the sources is made to better analyze the experiment. We refer to this consolidation in statistics as pooling. Note that sources are the factors and the interactions. In our case, we had 3 factors and 3 interactions, so we had 6 total sources. The pooling rules. The first rule, pull all sources into the residual that have F ratios that are less than or equal to 1. In our case, we didn't have any that were less than or equal to 1. Second, if after the first rule is completed, the total degrees of freedom for the unpooled sources is not half or less the total degrees of freedom for the original sources in the design, then more pooling is necessary. Well, what do we mean by all of this about degrees of freedom? Well, we started with 3 factors and 3 interactions, so that's 6. We only had 2 level settings, so we have 6 total degrees of freedom associated with those sources. So from a pooling rule standpoint, we should be combining 2 or 3 of those sources into the unexplained. But in our case, we had p-statistics that were 0.05 or less, or 95% confidence, and we have we've set that as our rule of thumb that says, well, if it's at a p-value of 0.05 or less, we're going to call it significant. So we don't have anything that wasn't significant, so therefore we're not going to be pooling. But that's not always going to be the case. Let's digress and take a look at the F statistic and how it leads us to the p-value. We're going to use an example here, and the example has one factor at 3 level settings with an n of 25, or 25 total data points. We've run this evaluation and we have our analysis of variance. The degrees of freedom is associated with the power of the test, and that's also driven by the number of data points. Our total degrees of freedom is one less than the total number of data points. We're going to conduct an analysis, so we have to pay. The degrees of freedom is our little piggy bank. Our factor has 3 level settings. We take away 1, leaving 2 degrees of freedom for the factor. The result is the unexplained, or the error term, has 22 degrees of freedom. The mean square is calculated by dividing the sum of squares by the degrees of freedom. We then calculate the F statistic, which is the mean square for the factor divided by the mean square for the error term, or the unexplained. That will lead us to the p-value. Presented in front of you is the distribution for this particular analysis. It's a distribution for F, the F statistic, for 2 degrees of freedom for a factor and 22 degrees of freedom for the unexplained. Let's look at a couple of values of note on our F distribution. The first is a value of 3.44. That yields a p-value of 0.05, or a 95% confidence that there is a difference when we change settings for our particular factor related to the outcome that we were measuring. For a value of 5.72, our p-value has now been reduced to 0.01, or a 99% confidence. Next, let's take a look at another value of note of the F statistic. If we have an F statistic with a value of 1 or less than or equal to 1, and what that tells us is that the mean square for the unexplained is as big or bigger than the mean square for the factor. So if the variation that's associated with the unexplained is as much or greater than the variation associated with the factor that we're trying to decide if it makes a difference or not, we have no more confidence in betting on the unexplained, so we should have no confidence in betting on that particular factor. So for a F statistic that turns out to be equal to 1, that gives us a p-value of 0.38. That's significantly larger than 0.05, and we've always said that we want to have p-values that are less than 0.05. If we have an F statistic of 0.5, we can see that the p-value is now leaped up to 0.61. So as our F statistics decrease, we see that the p-values increase. But as our F statistics increase, then we see that our p-values continue to get smaller and smaller and smaller, thus driving up the confidence that we have that there is a difference when we changed between settings for the particular factor that we were studying. Well, that's where the p-values come from, and they're based on the F distribution. Now that we know how to determine if a factor is significant, the next step in our analysis is to determine the best settings for those significant factors. To do that, we're going to go to Stat, DOE, Factorial, Analyze the factorial plots. The dialog that comes up allows us to select the main effects plot and the interaction plot. We then have to set them up. So the setup for the main effects, we select a response of boil time, and since factors A, B, and C were all significant, we're going to put them into the selected column. In the interaction plot, it's also going to be the boil time for response, and since the AB, AC, and BC interactions were all significant, we're going to select A, B, and C and put them in the selected side. Now we're ready to generate the plot, so just press OK and OK, and we'll take a look at what the plots tell us. Remember, we're trying to minimize the time it takes to boil a cup of water in a microwave. Here is the main effects plot that we use to select best settings. We have the cover, which is factor A, rotating, which is factor B, and location, which is factor C. For the cover, the least amount of time to boil a cup of water turns out to be yes, have it covered, with something less than 215 seconds. For rotating, yes, we want to rotate. That's going to give us the lowest time to boil a cup of water. And for factor C, we want to be 4 inches off center. That's going to give us the lowest value as well. So we want A1, B1, and C2 for level settings. Let's now take a look at the interaction plots because they were all significant as well. Here are the interaction plots that we're going to be able to use to select the best settings. Let's take a look at the first interaction between the cover and rotating, the AB interaction. We see that in this interaction, we want to have it covered and we want to have it rotating. So it's cover yes and rotate yes. For the next interaction, we have cover versus location. And we can see that we want to be 4 inches off center for C, the location, and we want to have it covered. For the last interaction, we have BC. So B says that yes, we want to rotate, and C for location says that we should be 4 inches off center. So that gives us an A1, B1 best combination, an A1, C2 best combination, and a B1, C2 best combination. We're going to use those to make a prediction to find out how fast we can actually boil a cup of water in the microwave if we use the optimal settings that we found in our design experiment. Now that we know which factors are significant and we've identified the best level settings, we can use this information to make a prediction about the expected results. In Minitab, we have a response optimizer. So to get that started, we're going to say stat, DOE, factorial, and select the response optimizer. The response optimizer builds a regression model based on the significant factors that were left on our model at the end of our analysis. The dialog box comes up and we select boiling time as our response to evaluate. We press the setup button and that gives us this dialog box where we can select either minimizing, hitting a target, or maximizing our response. In this example, we want to minimize the time it takes to boil a cup of water in the microwave. We're going to enter in a target value of 195, which we estimated, and then an upper value of 200. And then we can press OK. That brings us back to the original dialog box, and once we press OK, it's going to generate the regression model and you'll see the response optimizer. Here we have the response optimizer of results. Notice that our three factors are listed: cover, rotate, and location. It says high, current, and low. The current is actually the response optimizer's selected best settings. So you can see that for cover, we want to have yes, for rotate, yes, and 4 inches located off center. The red lines that you see associated with those in the graphic can actually be dragged back and forth between level settings, and it will change the prediction because this is a regression model. It allows us to play what if, and it works really well when you have continuous variables. So it may turn out that we want to actually be halfway in between a low and a high setting to give us a better expected response. So you can do that with continuous variables. In this case, we only had two settings and they're discrete, so there's no in between. The outcome that we're expecting to see is 196 seconds. So we should see our water boil if we cover it, rotate it, and put it 4 inches off center in 196 seconds or less. Now the D value that you see up here is a desirability index. It says our desirability is only 33%. That's okay. We put in a target value of 195. Now if we change that target value and we went back and reran our response optimizer, we could artificially increase the desirability index. So I don't put a lot of credibility in the desirability index because it's based on whatever we put in there for minimizing, maximizing, or targeting. And we may not actually know what the expected results are going to be until we run the optimizer. We can always go back to improve the desirability, but it's still not going to change what the prediction turns out to be. So in this case, we would expect to see the water boil in 196 seconds. We can make a prediction and put a confidence interval about it without using a regression model like the response optimizer. This is the by hand method, so let me show you how you do this. We're going to need a little bit of information. First, we want to review which factors and which interactions are significant. If the interactions turned out to be significant, they take precedent over the main effects by themselves. So in this case, we're just going to be using the level averages associated with the interactions. We see that the p statistic for the two-way interactions gives us a value of 0.002, so they are significant, they're guilty beyond a shadow of a doubt. Even though the main effects have a lower p-value, interactions take precedent always, always, always. Next, we'll take a look at the level average settings for those best combinations that we have in the interactions. So when we covered and rotated, we wanted yes, yes. That gave us a value of 207 seconds. When we had cover and the 4 inches off center, we saw that we had a boiling time of 206 seconds. And when we rotated and were 4 inches off center, we had a value of 209 seconds. Those are all the lowest level average settings that we had for all of the combined effects. Notice that they are lower than any of the single effects taken alone. Next, we're going to take a look at the descriptive statistics for boil time, because we're going to need that along with the residual error, which gives us 33 degrees of freedom and a mean square of 24.34. And then we need the overall average of all of the statistics that we had for boiling time. So the overall average of all the values we had in the experiment was 223.7. That's t-bar. It has a standard deviation of 13.98. We'll use that to generate a histogram to compare against our predicted histogram to see what the difference is. Let's go ahead and by hand make a prediction. So here is the prediction equation. Mu hat, which is the prediction, is equal to t-bar plus the sum of the significant factors or significant interaction best average settings minus t-bar. So actually what we're doing is we're looking at the incremental improvements over the overall average based on the best settings of the significant factors. And we only put significant factors in the prediction equation. In this case, because we had all significant interactions, that's all that's in the equation. We don't need to stick the main effects of A, B, and C in here because we've got them all covered with all of our combined effects. When we plug in the numbers, t-bar was 223.7, the A1, B1 level average was 207, the A1, C2 level average was 209, and the B1, C2 level average was 206. That results in a prediction of 175.3 seconds to boil 1 cup of water in the microwave based on using settings of A1, B1, A1, C2, and B1, C2, and the fact that we have significant combined effects of all of these factors. Now we're ready to put together the confidence interval, or the plus or minus values about our predicted condition. We predicted that we should be boiling water in 175.3 seconds. The prediction equation, our confidence interval, in this case it'll be a 95% confidence interval. So to calculate that, we take the square root of the F statistic with a 95% confidence interval, or a p-value of 0.05, for 1 degree of freedom for the factors and the degrees of freedom for the residuals. We're going to multiply that by the mean square for the residual, and then we're going to multiply that by 1 plus the sum of the degrees of freedom for all the factors that are involved in the prediction equation. We're going to divide that by the total number of data points. So from our analysis of variance, the degrees of freedom for the residual is 33, and the mean square for the residual is 24.34. Let's plug all this into our equation, and we'll come up with the 95% confidence interval about our prediction. Here's the F ratio table that we are going to use to interpolate our F ratio based on having 1 degree of freedom for a factor and 33 degrees of freedom for the residual. The residual degrees of freedom are the rows, and the columns are the degrees of freedoms for the factor. We can see that we have a 95% confidence F statistic listed for 30 and 40 degrees of freedom for the residual. Those values are in blue, and those are a 95% confidence or a p-value of 0.05. The values in red are a p-value of 0.01 or a 99% confidence. After we do our interpolation, we find that the F ratio for a p-value of 0.05, 95% confidence, for 1 degree of freedom for a factor and 33 degrees of freedom for the residual is a value of 4.139. We're going to include that value in our calculation. Let's go ahead and plug all the values that we have into our square root so we can calculate our predicted conditions confidence interval. For this example, we see that we have 4.139 for that F statistic. The mean square for the residual is 24.34. We had 3 interactions that were significant, that were part of our prediction condition. They each had 1 degree of freedom. So there's 3 total degrees of freedom. We add that to 1, giving us a value of 4. We had 40 total data points, and when we multiply that through, we're going to take the square root of 10.074, which gives us a plus or minus about that 175.3 seconds of 3.174. Now that's a 95% confidence interval about that 175 seconds. So what we can do is we can take a look at where should our values actually show up when we go to run our confirmation. Well, we should see our time in seconds somewhere between 172 and 178 seconds, and that would meet our requirement for validating our experiment at a 95% confidence. Now we can also calculate the standard deviation. We know that 2 standard deviations about the mean is 95% of our distribution. So if we have plus or minus 3.174 on either side of our mean of 175.3, that's equivalent to 2 standard deviations about the average, or 95% of the total population. So we divide the 3.174 by 2 to give us a value of 1.59. That's the estimate of the standard deviation. Now we can use that 1.59 standard deviation with our 175.3 to actually generate some data so we can compare the before and the after distributions just to see how much of an improvement we made from this design experiment. Here's a histogram that's showing the DOE data, which is the before data, and we're comparing it against the predicted condition, which is after the designed experiment. We can see that we've dramatically reduced the variability about the mean. We've also shifted the average value significantly lower than everything that we saw in the design experiment. So the overall averages that we had from all possible combinations was at 223.2 seconds with a standard deviation of almost 15. And we take the best conditions that we have based on the interactions, and now we would expect to see the water boil in 175 seconds with a standard deviation of around 1.7. That's a pretty significant improvement, and that's the difference between the before and the after, and you can see the benefit of a designed experiment. And now for your exercise, a helicopter design of experiments. You're going to be creating a 3-factor full factorial design of experiments on helicopter flight time. What you're going to try to find out is what's the best configuration of the helicopter that's going to maximize the flight time. As you can see, we've got all 8 experimental conditions shown here in this photograph. It's up to you to have fun with this, and we'll go into more detail on the next slide. You're now ready to conduct your helicopter DOE. The objective is to design an experiment that will allow you to analyze different helicopter configurations. The goal is to maximize the helicopter flight time. It should take you about 60 minutes. The factors and the settings. The underwing fold, yes or no. The body folded to a point, yes or no. And then body length, either full length or shorter. Design this 3-factor, 2-setting full factorial experiment in Minitab. Then you'll create all of your samples. There'll be 8 of them. You'll conduct the experiment, flying each helicopter multiple times, between 3 and 5. Analyze the results, and then you'll come up with a prediction, and you're going to create that helicopter that has all of the features that have turned out to be significant at the best level settings, and you'll make that helicopter, fly it multiple times, and then you'll be able to validate your predicted best settings. There will be a couple of videos that will follow this. One video will show you how to conduct the experiment. The other 2 will take you through Minitab to actually design the experiment, and then there'll be another one that will take you through the analysis of this particular experiment as well. So good luck on this. Take a look at those videos before you get started, and I think you're going to have some fun.